Hello, eighth grade. Sorry I couldn't be there today. My little guy Freddie is not feeling well, so I am home with him today. But hopefully we can still get some math going on here. This is our last lesson for our functions unit. In this lesson, we're just going to talk about how to look at real world situations, aka graphs, and interpret them. I know that you have been doing this a little bit in science with Miss Baumbach, because she has been asking me about it and whether or not what she has been talking about coincides with our math, and luckily now it does. So let's get started. We're going to interpret these graphs representing real world situations. So we're going to look at the graph and talk about what does that graph mean? What is that graph telling us? What do those X and Y values have to do with the function? How are the points on the graph representing that information? All that good stuff. Okay, so we have, I'm not going to do this warm up, piecewise functions. So this is a vocab word. It is a function made up of multiple functions, with each function applying to a certain interval of the main function's domain. That sounds like a lot of gibberish, but that's like if you had a graph, and let's say this X was time, and this was distance, and someone was like running really, really fast. And then they were like walking, and then they were slowing down. So the further they're getting away, the amount of time that they're running. Oh, that's not a great X value, actually. Sorry. So if it's distance, time, and this time is like, this one could maybe be like speed or something. But it's like they're running really fast, then they're kind of plateauing, and then they are running back home or something. So that's just showing like their intervals of rate of change and how fast they're going. So each of these little chunks of the graph is made up of a different y equals whatever function. Okay, let's get into examples because I think that will make this all make sense. So our first one here, sorry, we're going to skip through some of this. Liz drove to Aspen to go skiing. She skied for a while and then drove home. The graph at the right represents her trip. So distance from home is the y-axis. That's what goes up here. And the number of hours she was gone is on the x-axis. Find the rate of Liz's trip to Aspen in miles per hour. So this is her getting to Aspen, right? This is her skiing at Aspen, and this is her coming. So this is to Aspen, and this is home, and this is skiing. And the reason I know that is because distance from home increases, then the distance doesn't change at all because she's skiing. She's not getting further away from home while she's at the same mountain that she drove to. And then on here, she's getting, sorry. She's getting closer to home because her distance to home is getting closer to 0. So that is why I'm interpreting the graph into those 3 parts. So in this first one, find the rate of Liz's trip to Aspen in miles per hour. So we have to figure out what is the total miles she did. So the total miles, she went 150 miles. So that's miles. And we want to figure out how many hours did that take her. So it's kind of like that rise over run, right? So our rise was 150 and our run was 3 hours. But it's saying per singular hour. So when we are figuring that out, we want this to be over 1 hour. So 150 divided by 3, that'll be 50 miles in 1 hour. So that is her rate in miles per hour on her trip to Aspen. Okay. Now let's find the rate of her trip home from Aspen. So on the way home, she is still going 150 miles. She still is traveling 150 miles. And this time she goes from, let's see, this is kind of hard to draw. She goes from, I think I am not, if I had a ruler, I think it would make it a little bit better. Let's see, sorry, I'm going to erase some of these lines so that I can see exactly where it is. Okay, let's try to make our best. I think it's supposed to be at the 9. Yeah, if I draw my line well enough. So we have 1, 2, and then a half, right? So what didn't take her 3 full hours to get home, because this is definitely in between. So this is 2.5 hours. Again, if you guys weren't perfect on this, Miss Wright, it took her a while to draw the line too. I would maybe use a ruler if I was trying to do this perfectly. But I didn't. So in this case, again, we still want it to be per hour. So we still want it to be a unit rate. So we're going to take that 150. We're going to divide it by the 2.5 hours to figure out how many miles did you go in 1 hour. And we will get to 60 miles in 1 hour. So interpreting that graph is just taking each of the little pieces and figuring out what information those pieces are telling us. The last interpretation of this graph, how long was Liz in Aspen? How long was she not getting any further away from home? We know this first one, we said went 3. Oh man, that's hilarious. It told me that it was 9 up there. I didn't even need to try to draw the line. Okay. And we know that it goes to 9 here. So she was in Aspen from hours 3 to 9. So we're just going to subtract those two numbers to figure out how many total hours is it right here. So we're doing 9 minus our 3 to get that she was in Aspen for 6 hours total. So she got 150 miles away from her home. She skied for 6 hours, and then she drove the 150 miles home, and her trip total took 11 and a half hours. Okay. Okay, let's look at one more example, just interpreting some things. Hunter walked along the Pacific Trail until he came to a scenic spot where he ate lunch and read a book. Then he walked back to the start of the trail. So he started here. He walked distance from home. He went, it took him 3 hours to walk, 12 miles. And then he walked back, then he read a book. So this is his time for reading. Sorry. And then he walked home. His walk home took a lot longer, clearly. And he went from here, and this I think says 11. I'm going to guess down there. Yeah, 11. Okay, how far did Hunter walk along the trail until he stopped to rest? So how many miles, so that's this point here, did he get? So if he walked 12 miles because his rise, the distance away from home, is at 12, and the time it took because, and the reason we know this is because when we are writing ordered pairs, it is X first and then Y. And distance away from home, remember, the rise is always going to be the run. The rise is always going to be the Y value. So the rise is at 12. Find the rate of Hunter's walk in the scenic spot in miles, walk to the scenic spot in miles per hour. So miles per hour, we're going to put the miles over the hours because the miles are the Y, the hours are the X's. So we're going to put miles over hours. And then we're just going to take the numerator, we're going to divide it by the denominator to find that unit rate. So 12 divided by 3 gives me, it took 4 miles in 1 hour. That's how fast he was able to walk. Find the rate of Hunter's return walk. So on his return, he goes from 7 to 11 hours. So from 7 to 11, that's 4 total hours, right? Because if I do 11 minus 7, it takes him 4 hours. Does that make sense, hopefully? He still goes from 12 to 0. So his number of miles is still 12. So we're going to take that 12 and we are going to divide it by the 4 hours it took him to get home. Then we're going to divide those two again. So 12 divided by 4 is 3 miles per hour. Hopefully that was helpful in interpreting the graphs. We're going to do one more example here to talk about which graph fits the piece of information best. So they might give you a couple different graphs, and you kind of have to figure out which of these graphs is best for the example. So Tamara rode the Ferris wheel at the state fair. The Ferris wheel made 3 revolutions before stopping. Which graph below best represents Tamara's height above the ground based on the number of minutes she was on the ride? Okay, so these 3 graphs look completely different. The big things that we want to note here, this one, I think that some people would say, oh, this one looks great because it makes a revolution. She is turning in a circle. That's what we could maybe kind of talk about with that one. In example B, she's getting up to a height and then she's staying at that height for a while and then she's going down. So it's kind of like the Ferris wheel was levitating or staying in the spot. And then this last one, it looks like she's going up on the Ferris wheel and then she's coming down. And she's going up and then she's coming down. Then she's going up and then she's coming down. So in my talking through those opinions, in this first one, she's going up on the Ferris wheel and then she kind of goes backwards on the Ferris wheel and then she goes down. She goes up on the Ferris wheel, then she goes backwards, then she comes down. But a Ferris wheel doesn't go backwards. It just goes in like a circle. So it goes, she's going up, 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 down, 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 up, 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 down, 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 up, 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 down, down, down. So the Ferris wheel doesn't loop backwards. It's not going to roll on the ground. It is making a circle, but it's not also rolling like a wheel on the ground. That would be what this graph A was kind of showing us. So in this instance, they're just kind of talking through that. Graph C best shows Tamara's height after each minute. She goes up and comes down, then she goes up again and around the wheel. Graph B shows her getting to the top and sitting there, like the wheel isn't moving. So that's just like how you can talk through different parts of Tamara's ride. Let's look at one more here. Quinn played on the swings at the playground. Which graph below best represents Quinn's height above the ground based on the number of minutes she was swinging? So, Quinn played on the swings. So she's on a swing. The swing, are swings on the ground? No, most swings are not resting on the ground. Your feet might be on the ground, but your butt is not. So if we're measuring her height off the ground, we would typically measure from where the swing actually is. So the swing starts out here. She gets higher from the ground, then she gets closer to the ground, then she gets higher from the ground, then she gets closer to the ground. As we swing, our body is getting the momentum of the swing and we're pumping, we're getting further and further and further away from the ground. With each pump, the child is able to swing higher and higher and higher. So in this one, she started out and she got lower. Swings don't typically get lower to the ground from that starting point. That is their lowest point, correct? And in example C, she got higher and then she stayed. She levitated in the air and then she came back down. I don't know many swings that can stay up in the air. That would be super cool, but the swing is on like a pendulum, so it has to swing back and get further away from the ground. So in this case, I would say that B shows the best because she starts at a height, so she's not starting at 0, she's starting off the ground, and with each pump, she's getting higher and higher and higher and higher and higher. But every time she has to come back down, sorry, with all my lines on there, it's really hard to see. She has to come back down to the same point. You kind of see that there? Because the swing is always going to get down to that lowest point. because the swing has a lowest point on a pendulum when it swings back and forth. It's always going to come back down to that lowest point and then go up and then come back down and then go up, like kind of like a seesaw, or if you're like thinking and visualizing a swing in your mind. I was doing one with my hand, realized you guys can't see that. um, so the swing is kind of getting further away and then getting closer and then getting further from the ground and then getting closer to the ground. So that is why graph B represents it the best. So in this um, functions set of homework, you guys are just going to be looking at graphs. You're going to be interpreting that information, which might be calculating what is a unit rate for this, what is the rate of change, how fast was the person going, and then you might be picking a graph that best fits what the story problem is talking about. So you're going to do some practice problems today, and then bring them in on Friday so we can hopefully go over these together. So your homework is page 103 and 104, and you are going to do numbers it's going to be 103 to 105. My bad, guys. The first two pages only have 4 questions on it, so don't freak yourself out too much. So we're going to do numbers 1 through 14, and we're going to do all of them. Remember, there's going to be some where they're showing you a couple different graphs, and you kind of have to decide which of the graphs fits best. So just think through, what is that graph telling you? Look at the y and the x-axis, and what are those two axes actually telling you? If you have any questions, feel free to email me. I'm just home with Fred, and hopefully I can answer any questions that you guys might have.